Hi, this lesson is about differentials and linearization. So first let's talk about differentials and let's remind ourselves about some things we already know. So we know that we can find the slope of the line that goes through 2 points by computing the change in y over the change in x. And as the difference between the 2 points gets smaller, meaning closer together, we actually have our derivative, which we use the difference quotient formula and take the limit as h approaches 0, and that gives us the definition of the derivative. We know that f prime can also be written with this other notation as dy over dx, but when you look at it from this perspective, you can consider the dy and the dx separately as a ratio of two expressions, where dy is the differential of y and dx is the differential of x. So when you're asked to compute the differential of a function, instead of writing dy dx on the left side, you put the dy where the y is, and then you're going to put the dx to the right of the derivative. So you're still using all of your derivative rules, you're just keeping the dy and the dx on separate sides of the equation. So to find the differential of cosine of 3x, we need to use chain rule. So that'll give me negative 3 sine of 3x. But notice that here I have dy equals negative 3 sine of 3x times dx. Okay, so let's practice another one. Here we want to find the differential find the differential dy for y equal to the natural log of 3t squared. That's another composite function. So again, I used chain rule here. So I have dy equals 1 over 3 squared times 6t being the derivative of the inner function, times dt. So when you simplify the 1 over 3t squared and the 6t, you get that dy equals 2 over t dt. All right, let's try another one. We want to find the differential dy for y equal to x squared sine of 2x. So I have dy on the left. Didn't mean to do that. Dy on the left, dx on the right. But on the left side, on the right side, I have to apply product rule. And within product rule, I have chain rule because sine of 2x is a composite. So here we have f g prime plus f prime g. And then the only thing I did from the second line to this third line here is that I factored out a 2x from the two expressions inside the bracket. So you have that dy is equal to 2x times x cosine 2x plus sine of 2x multiplied by dx. All right, so when do we use differentials? We can use differentials to estimate dy, and we can also use them to compute errors. So first, let's practice some examples of estimating delta y. So dy is used to estimate delta y. Delta y just means that you're subtracting two function values, two y values. And dy will give you an approximation of what that calculation would be. And the way you use dy is that you take the derivative of the function, you evaluate it at the point, the first point of your delta y, and then follow it by your dx. Now, something to keep in mind is that your dx and your delta y will be equal to each other as long as your delta x is a very small number. So the delta x has to be approaching 0. And if that's not true, then your dy isn't going to give you a very good approximation. So the dx has to be small. So I just wanted to point out that this formula looks a lot like the point slope formula, which is right here. So y minus y sub 1, that's the delta y part of the formula. And then the m, well, we know that m is f prime, so that's this part. And then x minus x sub 1, again, that will be delta x, but your delta x is dx when the difference between the two x coordinates are small. So that didn't just come out of the blue. It's based off of something that we've already understand and have used before. All right, so here we're going to show that we can compute delta y and dy for this function, y equals e to the x, given that x sub 1 is 0 and the difference between x sub 1 and x sub 2 is 0.4. So I'm going to compute both the delta y and the differential dy to show you that we get similar results. Okay, so let's do the delta y right here. All right, so in order to plug in delta y, I have to figure out what x sub 2 is. What is the second coordinate that gives me a delta x of 0.4? All right, so here I have delta x is x sub 2 minus x sub 1. We know that delta x is 0.4. We know that the first coordinate is, or the first x variable is 0. So x sub 2 is also 0.4. So we plug in 0.4 here. We plug in the 0 here. You would need a calculator to compute this. And so we get delta y is about 0.492. Now let's see what our dy gives us. dy is the derivative of y, which is e to the x, and the derivative of e to the x is e to the x, times the differential dx. All right, we always start with the initial value. So my dy is e to the 0 times your dx, which is delta x. That's a small number, so it qualifies as a decent approximation. So you plug in 0.4 in for dx, and you get that dy is 0.4. So, I mean, they're not that far off. It's not a great approximation, but the smaller this number is, the better your dy will approximate the actual value of delta y. Okay, so you could have done this one without a calculator, and oftentimes when you're using dy to compute delta y, it's really for convenience. You get a decent approximation without having to rely on technology like we did here. All right, so let's go on. Let's do another one that's similar. We want to compare the values of delta y and dy for this third degree polynomial. And we were given that x changes from 2 to 2.01. So here my delta x would be small. So that's good news. All right, so my computation of delta y would be to plug in 2.01 into the polynomial and then plug in 2. Again, that one probably would be something that you'd need a calculator for, although you can cube 2.01, but just for convenience, you get 9.140701 minus, and then when you plug in 2, you get 9. So your delta y is 0.140701. Now let's compare what we get with dy. So remember, dy is the derivative of your function. So your third degree polynomial's derivative is 3x squared plus 2x minus 2, followed by dx. All right, my initial value of x is 2. So you plug that in here in the next line. And my dx is the difference between these two. It's your delta x, which is 0.01. So when you compute this, you end up with 0.14 as an approximation of your delta y. This is a pretty good approximation. And that's, again, because these are close. Okay, so as I mentioned before, you could also use differentials to compute error in a calculation. So here's an example. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? All right, so you're told that you computed a radius of a sphere to be 21 centimeters, but there's a possibility of an error in your measurement of at most. So not more, it could be 0.05 centimeters or less. Okay, so errors happen a lot in science. It could be a human error, it could be a calibration error, something wrong with the equipment. So there's a lot of reasons why you could have error, but errors could have serious consequences. So it's important to understand how errors could impact outcomes. So the question is, how can that error in radius, in the computation of radius, actually impact the computation in volume? All right, so we're going to use differentials to do that. First, we need the formula for volume. So V is equal to 4/3 pi r cubed. Then we take the derivative or the differential on both sides. So I have dV is equal to, and the derivative of volume, you're using power rule. So it's 4/3 pi times 3 r squared followed by your differential dr. So the 3's will cancel. The 3 in the denominator of 4/3 and this one cancel each other out. So you get dV is equal to 4 pi r squared dr. All right, now we can plug in numbers that we know. Radius was given to be 21. The maximum error, or the differential for radius, is 0.05. And so I use the calculator to compute this. So your differential in volume is about 277 centimeters cubed. So although the error in radius is rather small, it has a rather large possible error in volume. Okay, so let's move on to linearization, also called linear approximation. So they mean the same thing. So we can estimate the value of a function by using the linearization of a function. And the linearization of a function looks a lot like how we found the equation of a tangent line to a curve. So linear approximations means to estimate the area on a function at some value that I'm going to call a, when the difference between two x values is small. So, and again, that means that delta x is dx. And the linearization formula is L of x is equal to f of a plus f prime times of a times x minus a. And this linearization formula gives me an approximate value to the actual function. So this will be a line, but this will be some other function. So this formula, again, this one here, comes from the point slope formula. So again, I want to point out that it's not just something random. Remember, this is your point slope formula. And if I wanted to solve the point slope formula for y, I would add the y sub 1 over, and I would expand, distribute, combine like terms, but initially this is what you would do. You would move that y term over. So remember, this is the formula that I just gave you. So the y sub 1 is your function value at a. The m is your derivative at a. And x minus x sub 1, well, that's x minus a. So just assume that your point is a f of a instead of x sub 1, y sub 1, and it really is the same formula. And this allows you to approximate some function value. It's not an exact answer. All right, so let's do an example. So we want to determine the linearization of the function y equals 4x cubed minus 2x at a equal to 1. So at first we're just going to find what the linearization is. Then I'll show you how that linearization will allow us to approximate values. All right, so we need to know what your function value is at 1, and we also need to know what the derivative is at 1. So when you plug in 1 into 4x cubed minus 2x, you get 2. When you take the derivative, you'll get 12x squared minus 2x, minus 2. So when you plug in 1, you'll get the value of 10. So we know that f of 1 is 2, f prime of 1 is 10. Your linearization will be f of 1, which is 2, plus the derivative 10 times x minus a, which is 1. And if you distribute and combine like terms, your linearization is the line 10x minus 8. So your linearization will always be a linear equation. All right, so we want to find the linear approximation, also called the linearization, of the function f of x equal to the square root of 1 minus x at the value of a equal to 0, and then use that linearization to approximate the square root of 0.9 and the square root of 0.99. Now, these two radicals are irrational numbers. They are not perfect squares. So you would need a calculator to get an answer for that, but we're going to use this technique to get a pretty decent approximation of what those two numbers are. All right, so first I rewrote f of x as 1 minus x to the 1/2 so that I can now use my chain rule to take the derivative. So you take the derivative, outer function is 1/2 1 minus x to the negative 1/2 times the derivative of the inner function, and that derivative is negative 1. All right, so now I can evaluate both f of x and f prime at a equal to 0. So when I plug in f of 0, you get it's equal to 1. When I plug in f prime of 0, you get f prime is negative 1/2. All right, so now I'm ready to plug into my linearization. L of x is equal to f of 0 plus f prime of 0 times x minus 0. So that's the formula that I talked about above. So we already did the work, so just plug in the numbers. So you get L of x is 1 minus 1/2 x. Remember, any function value will be approximately equal to whatever this line provides. So now I have to use it to approximate the square root of 0.9. Okay, but that doesn't mean that the x value is 0.9. Remember, the function is the square root of 1 minus x. So how would my square root equal 0.9? It would be 1 minus 0.1. So 1 minus 0.1 is 0.9. So that means that my x value is 0.1. So now that's what I plug into my linearization. I'm going to plug in 0.1 into the line, which is what I did here. And again, this could be done without a calculator. This is just 0.5 times 0.1, which will give me 0.05. So when you subtract 1 minus 0.05, you get that the approximate value of f of the function at 0.1 is about 0.95. And if you actually took a calculator and plugged it in, it would give you this as an answer, 0.948683. So 0.95 is actually a pretty good approximation of that square root. So we're going to repeat the process. I'm going to use that same linearization equation that I found to approximate 0.99. Again, remember the function is 1 minus x. So what is x for that radical to equal 0.99? It has to be 0.01. So my function, I'm plugging in 0.01 into my line, which is what you see here. So I have 1 minus 1/2 times 0.01. Again, you don't need a calculator to compute that. So you get 1 minus 0.005. So your line tells you that the approximate value is 0.995 for square root of 0.99. Okay, but if I compare this to what the calculator says, again, just putting 0.99 and taking the square root, it gives me 0.994987. Again, pretty good approximation by using the linearization without requiring technology to compute that. In both cases, both the 0.9 and the 0.99, the linearization was slightly higher. So the approximations are overestimates. And that's because of the way that the graph is. So your 1 minus, the square root of 1 minus x is the one here in this red or hot pink color. But the line 1 minus 1 half x is this blue line. So you can see when I'm at 0, which is what a was equal to, and I'm looking at values close to 0, like 0.1 and 0.01, my line goes very close to the curve, but it's always slightly above it when you are close to this point. So we're not actually on the point, we're close to it, which is why it was 0.01 and 0.1. They were both close to a equal to 0. Okay, so we're going to do another one that's similar in terms of using linearization to approximate. So we want to use linear approximation to estimate the value of 2.001 to the 5th power. All right, so we're actually given a little bit less information here. We just know what we want to approximate, but we need to come up with the function. So it looks like our function is x to the 5th. So the derivative is 5x to the 4th. Now, it would make sense for the initial point to be 2, because it's easy to raise 2 to the 5th power. It's also easy to evaluate 2 here, and 2 is certainly close to the value that we want to approximate. So it's not quite as easy to compute 2.001 to the 5th power by hand. So linearization will allow us to do that. So I have my function and my derivative, and I plug in 2 into my function. I get 32. I plug in 2 into my derivative, and I get 80. Remember, that is the slope of this line that we're finding. So L of x, according to the formula, is f of 2 plus f prime of 2 times x minus 2. So we know that f of 2 is 32. We know that f prime of 2 is 80 times x minus 2. Distribute and then combine like terms. And so we get the line, the linearization is 80x minus 128. All right, so now this one's very straightforward. If the function is x to the 5th, my x is 2.001. So you plug in 2.001 in this line. Again, that's something you can do easily without a calculator, and then subtract from 128, and you get that the linearization tells you that 2.001 to the 5th power is about 32.08, which sounds like a pretty reasonable number because I know that 2 to the 5th is 32. But if you plugged it into a calculator just to compare, this is what it would tell you. And so you can see that these numbers are very close. The 32.08 is a very accurate approximation. And in this case, my L of x is a slight underestimate to your linearization. So graphically, x to the 5th would be slightly below the line that we found here when you're close to 2. Okay, so that's the lesson. Give the homework a try. Good luck.